Hi there, folks. In today's lesson, we're going to be looking at theoretical and experimental probability. And when we're talking about probability, probability is how likely an event is to occur. Basically, we're talking about how often this is going to happen. And when we talk about theoretical probability is essentially what the probability should be. Okay. Basically, we take the number of favorable outcomes over the total number of possible outcomes. In other words, how many ways can this thing happen over the total number of possibilities? That's the theoretical probability. And again, theoretical probability is what the probability should be. Okay, it's the ideal probability. And so we talked about the probability of the event is basically how many ways that event can occur over the total number of possibilities. All right. For example, if we look at some real simple ones here first, if you roll a 6-sided die, what is the probability you will roll a 3? All right. So this time I'm looking for the probability that we're going to roll a 3. And on a 6-sided die, when I look at those sides, there's only one possible way that I can roll a 3, and it's by rolling a 3. There is one 3 on that die. But if I were to roll that 6-sided die, really, there's a total of 6 possibilities, so the probability is 1 out of 6. There's one way that I can get a 3 out of 6 total possible options. Okay, so it's 1/6. If I look at the next one, it says, what's the probability you will roll an even number? Okay, so an even number. So this time I want the probability that I'm going to roll an even number. So I think about how many even numbers are on a 6-sided die. I've got a 2, a 4, or a 6. So there are 3 options for rolling an even number. There's still 6 total possibilities when I roll that die. And now I'm going to reduce the fraction to 1/2. All right, very simple stuff. If I look at the next one, what is the probability that you will roll that you will not roll a number greater than 2? So numbers that are not greater than 2, so probability that it's not greater than a 2. Well, there's 2 numbers that are not greater than 2, a 1 or a 2. Right? So there's 2 possible options for getting a number that's not greater than 2. There's still 6 total options, which reduces to a 1/3. And that's it. Okay? If I look at something like this, a bowl contains 12 slips of paper, each with a different month on it. And if I pull one slip of paper out of this bowl, I want to know what's the probability that I pull a month that begins with the letter J. All right, so I have to think about the months that begin with the letter J. So I've got months like January begins with a J. I've got June, also begins with a J. And I've got July that begins with a J. And I think that's about it, unless one of them changed and I wasn't aware. So it looks like I have 3 months that begin with the letter J. So there are 3 months that start with the letter J. 3 ways that I can make this happen. Over 12 possibilities. There's a total of 12 months in this bowl, and that reduces to a 1/4. Okay? If I look at the next one, I want months that end with a Y. So as I work down through this, once again, January, that one's going to end with a Y. February also ends with a Y. March, April, May is the one that people tend to forget here. May ends with a Y. July is the next one that ends with a Y. And as I work down through the rest of the months, I believe that's it in terms of months that end with a Y. So it looks like there are 4 months. So there are 4 months out of the 12 total. So there's 4 ways that this can happen out of 12 total options, which is a 1/3. Okay? The probability that a month has exactly 30 days in it, they pull one with exactly 30 days. And if you're not sure about your months, you can look at a calendar here. But we've got September, April, June, and November are the 4 that have exactly 30 days in it. Everything else has 31 days except for February, of course, which only has 28 or 29 on a leap year. So right here, I've got 4 months that fit this criteria, so there's 4 ways that this can happen over a total of 12 months, which reduces to a 1/3 once again. Okay? If I look at this one, the probability that has less than 28 days in it, well, there is no month that has less than 28 days in it. They all have 28 or more. So there are 0 months that are going to fit that criteria out of the 12 total, which means there is 0 chance that I will find a month or I will pull out a month that's got less than 28 days total in it. Okay? If I look at something like this, a jar contains 5 green, 10 red, and 7 blue marbles. I want to know what's the probability of pulling a red marble. So the probability that it's going to be a red marble Well, there are 10 red marbles, and there are a total of 22 marbles here, 5 green, 10 red, and 7 blue. So a total of 22 marbles. So the probability is 10 out of 22. Again, I have to reduce my fraction to the 5 over 11. Taking a look at the next one, the probability of pulling a green marble. I want the probability of a green marble this time. So the probability of a green marble, there's 5 green marbles. If I remember correctly, yep. Out of the 22 total. So it's 5 out of 22. Once again, I go to reduce my fraction. This one doesn't reduce. So I'll leave it the way it is. It's 5 out of 22. Okay. The next one, the probability of pulling a marble that is not blue. So this time I want the probability that it's not blue. And there's a couple ways we can approach this. If I think about not blue, well, not blue means it's one of the other colors, so the red or the green. And there's a total of 15 other marbles other than the blue one, so that's 15 out of the 22 total. And then I would reduce that fraction, which this one doesn't reduce, so it's 15 out of 22. The other way I'd like to think about this for a moment is if I think about the probability of pulling a blue marble. The probability of pulling a blue marble, there's 7 blue marbles out of the 22 total. So the probability of pulling a blue marble is 7 out of 22. So not blue is 15 out of 22. And the thing you should notice about those fractions is that they add up to 1. They add up to a 22 out of 22. And when you think about 1 is like 100% probability. Well, obviously not blue versus blue has to add up to 1. Okay? So the sum total of all of our probabilities should always add up to 1. And that's the point of looking at something like not blue. Okay? So the probability of blue is 7 out of 22. Probability that it's not blue is 15 out of 22. Okay? Very similar with the next one, the probability of pulling a marble that is not green. So the probability that it's not green, again, I could count up all the stuff that's not green, or I can think about the probability of it being green. The probability of it being green, I believe there was 5 green marbles. Yep, 5 green marbles out of the 22 total. So if 5 out of 22 is green, not green would be everything else, which is going to give me a 17 out of 22. Okay? For the next one, anytime we're given values like this, here I have area that I'm looking at. I want the probability of hitting a bullseye if the distance between the rings is 2 inches. Okay? In other words, the distance from here to here is 2 inches, the distance from here to here is 2 inches, and the distance from here to here is also 2 inches. Okay? And basically, if I'm looking at the probability of hitting the bullseye, I want to know about hitting this little area right in here. Okay? So I want to find out how can I hit that area right there. So basically, what I'm looking at here is I'm looking at area. So when I want the probability of hitting the bullseye, I need the area of the thing I want, that little circle in the center, which when I look at this little circle in the center, it's got a diameter of 2, which means it has an area. Area of a circle, remember, is pi r squared. So it has an area that's pi times r. Well, the radius of that little circle is 1. Okay? That's the area of this little circle right in here. Okay? And if that's the area of the thing I want, I need to put it over the total. So I do the area of the entire thing. And again, when I think about the area of the entire thing, I need the radius here. And there's 2 ways to think of the radius. You can count it up and see that it's 5. Or look the whole way across. If this is another 2 inches and another 2 inches, the whole way across here would be 10. So the radius here is 5. So it's pi times 5 squared. Okay? That's how I find these. When I'm talking about objects or shapes, I do the area of one thing over the area of the entire thing. Okay? The area of the piece I want to hit over the area of the entire thing. And now I'm going to simplify this. And right away, we should notice that the pi's cancel out. 1 squared is 1. 5 squared is 25. So it looks like the probability of hitting the bullseye, assuming that I hit the target itself, is 1 out of 25. And when you look at the little area that's in there, when you look at that tiny circle in the center, if you were to picture 25 of those, it would be about the size and shape of the overall circle. Okay? The last thing we need to look at is experimental probability. Experimental probability is essentially the probability that we observe through a certain number of trials. Okay? So theoretical probability is kind of what the probability should be. Experimental probability is what we actually get when we do the things that we're talking about. Okay? For example, if a spot checker at a rubber chicken factory, because that's a thing, inspects 500 chickens per day, if 10 are found to be defective, I want to know what is the probability that a rubber chicken is defective. Okay? If I was looking at theoretical, I'd be looking at what should the probability be before I do this thing. Now experimental, I've actually gone through this. We've made rubber chickens, and we found out that 10 were defective. So the probability that I have a defective chicken, there were 10 defective ones out of 500 total. Okay? Experimental probability is just what we get when we actually do this thing. So it looks like a 1 out of 50. And I'm going to write experimental probability as a percent. It's just an easy way to distinguish between experimental and theoretical. Theoretical probability I will always express as a fraction, a reduced fraction. Experimental probability I'm going to express as a percent. So 2% of the rubber chickens are going to be defective. And that would allow us to make predictions about future values of these things. If I was looking at a batch of 50,000 of them, I could calculate how many we would expect to be defective. Okay? If I look at something like this, 20 kittens are strapped to parachutes and dropped out of a plane. 17 make it to the ground unharmed. And I want to know what is the probability that a kitty goes splat. Okay, so here we go. The probability that we're going to get a little bit of a splat. It's a good thing we're testing these parachutes before we give them to human beings. That's all I'm saying. So if I look at something like this, I've got 20 kittens strapped to parachutes, 17 make it to the ground unharmed. So the probability that they're not going to make it here, if 17 made it to the ground unharmed, it means that 3 of them did not make it to the ground safely. And that was 3 out of the 20. And again, I'm going to express this as a percent just because it's a experimental probability. So I get about 15%. Okay, so this parachute company is not doing something well if they are only getting if they have 15% of the parachutes are not working properly. Okay, so again, theoretical probability is what the probability should be. How many ways can I get this thing over the total? Experimental probability is what did I actually get? How many of this thing did I get over the total number of trials performed? Okay?